Hello again, calculus students. The topic for today is graphing functions. So piggybacking on what we learned in the previous lesson about how we can use the derivative to extract fine details of a function's behavior, we want to translate that information into graphical form today. So we can put all of that information together about where a function is increasing, where it's decreasing, where it's been upward, where it's been downward, where it has peaks and troughs, where it has inflection points, and information about the end behavior of the function. Like what's it doing on the extreme far right, the extreme far left. We can learn about asymptotes from limits. We can put all of this information together to piece together a pretty fine graph of a function. No doubt you wonder why we want to learn such a skill in today's technologically driven world. Surely, can't we just use graphing calculators and apps and things of that sort? Well, we can, but it turns out that those graphers and apps don't give the fine detail that we can extract by hand. So the idea is that if we use the calculus and learn some things by hand and then double check that and compare it to automatically generated graphs through apps, that we'll gain a fuller understanding of how the function behaves.
Hello, calculus students. Today we're going to talk about graphing functions. This may seem like a bit of an old-fashioned thing to do given that there are so many apps and devices that can do graphs for you. Really the point of this is to get you to understand how functions behave. So by sort of doing something with your own hands, you're going to learn a lot more about how functions behave. It also has some practical value too. Just plugging things into a grapher sometimes give you some misleading results. So if you can back what you're seeing from the computer up with some analytical results and know how to interpret it, you're going to be better able to interpret how the function behaves. I copied from the textbook here some guidelines for graphing a function. I don't want to sit here and read all of these instructions, but maybe I'll quickly go over them. So the first thing to do is to make sure you understand the domain of the function. That just makes sense, right? What part of the x-axis are you going to graph the function over? Part 2, exploit symmetry. I don't know how big of a deal I think this is, but if you know a function is even, f of negative x equals x, then you know that it has symmetry over the y-axis. So something like a parabola with a vertex somewhere on the y-axis would have this property. If you notice it, it's fine. If not, it's not a big deal if you exploit symmetry. Maybe it saves you a little work if you really think about it. The third step here is to find the first and second derivatives. Yes, very important because you're going to use the first derivative to figure out where the function is increasing and decreasing. You're going to use the second derivative to figure out where the function is concave up and concave down. And this is pretty important to seeing the shape of the graph. Finding the critical points and possible inflection points. This typically amounts to setting the derivative equal to 0 and the second derivative equal to 0. You also have to think about where the first and second derivatives are undefined to get these points. The fifth step, find the intervals on which the function is increasing and decreasing and concave up and down. So you do this with number lines, and you put the critical points and or the possible inflection points on a number line, and then you check the signs of the intervals. Identifying extreme values and inflection points. So if you see that the sign of the first derivative changes at a critical point, then you'll know that you've either got a maximum or a minimum, so it's kind of nice to make note of that. And inflection points are just those places where in the domain of the function where the second derivative changes sign. That helps you to see the shape of the graph, the way that it's bent changes. Of course, identifying any asymptotes. So if you notice that you're getting division by 0 in the function, you know you're going to get an asymptote there. In behavior, just, you think about what happens when you plug in a really big value of x, either positive or negative, and you want to think about whether you're having a horizontal asymptote or is the function just going off to infinity. Finding the intercepts give you a little bit of information about pinpointing how the graph looks. So it's pretty easy to figure out where the graph crosses the y-axis. That one's easy. You just put in x equals 0. You can also try to find the x-intercepts if it's convenient, because if you take the original function and you set it equal to 0 and solve for x, those will be your x-intercepts. Those may or may not be easy to find though. And then choosing an appropriate window. Well, I think that'll be obvious. After you've done all the steps above, you're going to know where all your critical points are and these things, and that'll sort of determine what size window you should use along the x-axis. And then getting sort of the scale you need on the y-axis will depend on things like where it crosses the y-axis and what the y values are at some of the important points on the graph, like at the maximums and minimums and at the inflection points and things like that. So the size of the window will emerge from this process. And then one thing, I put a note down here that the sign of f prime and f double prime can change at x values where f is undefined. So points that are not in the domain of the function are not considered critical values or possible inflection points, but the behavior of the function can change around these points. Like the function can change from concave up to concave down on either side of an asymptote. So you do want to keep track of those places where the function is undefined, especially if they're sort of isolated locations like you would see at asymptotes. Okay, and so we'll want to put those x values on your sine charts. So with all this in mind, I think it'll just be helpful to see a few examples and how you would do this. Now I urge you're setting out there on your computers and your immediate reaction is to go, why don't I just graph this thing first? And then I'll just try to fake it by sort of making my graph match the one that I see on the computer. You're missing the point if you do it that way. The point of this is to take what you've learned about how the derivative is related to the behavior of the function and see if you can get the behavior of the function analytically. And then after you have an idea of what that graph looks like, then you might plug it into a computer and see if it confirms your result. But if you go the other way, you're never really going to see if you're doing these things correctly or not. So let's start with this example. The function is x cubed over 3 minus 400x. All right, so what is the domain of this function? Well, this is a polynomial function, and polynomials have a domain of all the real numbers. And so our domain here is just negative infinity to positive infinity. All right. And then next, we need the first and second derivatives. In the first derivative, bring the 3 down, I'll have x squared minus 400. And then the second derivative is 2x. Okay, so now on the left over here, let's figure out the places where f prime is equal to 0 or undefined. Well, f prime would be equal to 0 when x squared minus 400 is equal to 0, which would happen if you add 400 to both sides, take the square root, you're going to get x is plus or minus 20 here. And also, the first derivative is never undefined, being a polynomial. Okay, second derivative equal to 0 undefined. Well, the second derivative is never undefined, so it's just going to be where is the second derivative equal to 0, and that's pretty easy to see. That's when 2x is equal to 0, and solving that for x, you get x equals 0. All right, so already we're quickly gaining some information about this. We've got the domain of the function here. We know we've got to graph this thing over the whole real number line. We've got our first derivative, which we're going to have to keep our eye on. And we've got our second derivative here. And then we've got these points that we need to be paying attention to. X equals plus and minus 20, where the first derivative is equal to 0. So these are going to be the places where maybe our function changes from increasing to decreasing or vice versa. And we've also got this x equals 0, which is a possible inflection point. So that's the place where the function may change from concave up to concave down or vice versa. So let's make a sign chart for f prime and f double prime. I think we could do this on one number line here if we are careful about it. Try to be neat. Okay, let me put the places where f prime was equal to 0 on this number line. Let's say here and here. So that's negative 20 and positive 20. And let's put the places where f double prime was equal to 0 on this number line. That only happened at x equals 0, so let me put that right about there. And then on the top side of this number line, I'm going to check those intervals for the sign of f prime. Now f prime was x squared minus 400. If I plug a number to the left of negative 20 into the first derivative, say negative 30, well, I would get 900 minus 400, and that's positive. So the sign of the first derivative is positive on that interval to the left of negative 20. And then if I plug a test point between negative 20 and positive 20 into the first derivative, let's say x equals 0, I get negative 400. So that sign is negative. So the first derivative is negative between negative 20 and positive 20. And then if I plug a test point to the right of 20, let's say positive 30, I would get 900 minus 400. That's positive. So here's my sign chart for the first derivative on the top side of this number line. And on the bottom side, I need to plug in a couple of test values for this, but into the second derivative now. So if I would say plug negative 1, which is to the left of 0, into the second derivative, I would get negative 2. So we're minus over here. And then if I plug test point of 1 into the second derivative, I get positive 2. So the second derivative is positive over here. So there's my sine chart for both of the derivatives. Now we could look at in behavior. So what do we mean in behavior here? So one way to check the in behavior of function is just to take the limit as x goes to positive infinity of the function. So in this case, our function is x cubed over 3 minus 400x. And if you remember your lessons on limits, as x goes to infinity, we see the dominant term in this thing is x cubed, and so we can easily see that this is going to positive infinity. And similarly, we can look at the x going to negative infinity of this function. And since the dominant term is x cubed over 3, and if I put in a big negative number, I'm going to get an even bigger negative number back. So this one's going to negative infinity. So this is telling me what's happening to the far right on the graph and the far left on the graph. There aren't any horizontal asymptotes. It's just going up on the right and then down on the left. And then we could think about vertical asymptotes. We know that vertical asymptotes are values of x where the function goes to either plus or minus infinity. And these always happen, or typically happen, at places where you're getting division by 0. But these are the function we're dealing with here is a polynomial. It doesn't have any vertical asymptotes. So let me just write none here. Let's identify some of these special places on the function. So local extremes. So these are either local mins or local maxes that we see from the first derivative test. Now if we look at the sine chart for the first derivative up here, I can see at negative 20 the function's going up and then it starts going down. So the sign of the derivative changes from positive to negative. The first derivative test tells me then that there will be a local maximum there. And similarly at x equals positive 20, the function's derivative changes from negative to positive, so that means there's going to be a local minimum at x equals 20. And let me put the coordinates there. So if x is 20, what would the y coordinate be? Well, I just have to put 20 into the original function. Right? So what's f of 20? That would be 20 cubed. 8,000 over 3 minus 8,000. So that'll be negative 2 times 8,000 would be 16,000 divided by 3. So maybe just to get a sense of that decimal value, that would be negative 5,000. Let's see, 3 into 16,000. 3.3 repeating. And similarly, we'll have a local maximum at x equals negative 20 because that's where the sign of the derivative changed from positive to negative. And so let's see what we get there. So we need to do, what's f of negative 20? So f of negative 20, well, that would be negative 8,000 over 3, and then plus 8,000. So it's a very similar computation to the last time, except this time it's going to be positive. So this one will end up being a positive 5333.3 repeating. Okay, let's see from our sine chart on the second derivative, do we have any inflection points? Yeah, we see at x equals 0 there's an inflection point because the sign, that's a point in the domain of the function, and it's where the sign of the second derivative changes. So the second derivative, I just want to see what is f of 0. F of 0 is 0. So we know 0, 0 is an inflection point. Let's see if we can determine x-intercepts easily. So x-intercepts are where you just take the whole function and set it equal to 0. So if I take x cubed over 3 minus 400x, it's easy to set that equal to 0 and solve. And maybe it's not so bad. If I multiplied through by 3 and factored out an x, it'd look like x times x squared minus 1200 equals 0. So at x equals 0 and x equals plus or minus the square root of 1200, which is 100 times 4 times 3, so that'd be 10 times 2 is 20 squared root of 3. And we can punch that into a calculator to get the decimal value of it. But yeah, we have x-intercepts at x equals 0 and x equals plus or minus 20 squared root of 3. And the y-intercept would be, just means put x equals 0 in the original function. And when you do that, you just get y equals 0 also. So 0, 0 is the y-intercept. So, okay, I think we have enough information to try to graph this thing. So let me make a set of axes over here. Okay, so we have these local extreme values at plus and minus 20. So maybe I'll make the scale on the x-axis so that about here is negative 20. And about equal amount to the right is where positive 20 is. And I know at negative 20 I have a maximum, and its height is at some big number like 5,300. So let me just put that number out here. 5333.3 repeating here, and then a negative amount down here. I think that'll capture the size of my window well enough. Let's see, so we have a maximum here at this point, negative 20, 5,300. And I know, so I'm just going to draw a little bit of the graph there. I know that it's doing like this there. And then similarly, I have a minimum out here at x equals positive 20. So I'm not going to draw a lot of the graph there. I just want to draw like enough to indicate that, there's a maximum there, or a minimum there. Now I know that the graph goes through the origin because that's the y-intercept. It's also one of the x-intercepts. And it's also an inflection point. And in fact, the inflection changes from, if we go back up here and look at the sine chart for the second derivative, we see to the left of 0 it's concave downward, and then to the right it's concave upward. So I think I'm starting to get a pretty good sense of what's going on with this graph. So let me erase these little bits of the graph here so I can get a little bit more accurate of a picture. It's concave down until it gets to the origin, and then it starts to bend upward until it gets to this minimum. And now on the left-hand side of the graph, it's going to go down, and it's going to keep going down forever because of what we know about the end behavior. So really the last thing that I can put on here is what the intercept is. And the intercept was 20 times the square root of 3, so that's 20 times 1.7 or so. So I can see I probably need to extend my x-axis out here a little bit further. So it's not quite negative 40, but somewhere out here is, let's say about there, is negative 20 square root of 3. And similarly on the right-hand side of the graph out here, I've got positive 20 square root of 3. And so the graph is going down, hits that x-intercept, then it keeps on going down. And then similar behavior on the right-hand side. It goes to that intercept and keeps on going up like that. I think that's a pretty good representation of the graph. I've got the region where it's concave down from negative infinity all the way to the origin reflected in that graph. Then it's bent upward to the right of the origin. I've got the local extrema identified on the graph here. So maybe we can label some of these points. Negative 20, positive 53.3 repeating, 0, 0, positive 20, negative 5,333.3 repeating. Yeah, I think we're looking good. So it would be kind of fun to now let's check our work and see if our analytical results match what the grapher says. So let's pull up Desmos. Okay, so as you can see, after I punched in x cubed over 3 minus 400x, it looks like I'm not even getting a graph. I see kind of a red line there. Is that just the y-axis? I don't know. Well, we know that on our graph, we really need to see from negative 20 to positive 20 on the x-axis, so let's at least get it out that much. But we also know that the y-axis needs to have a scale that goes, over 5,000, right? That looks pretty close to what we thought it should be. Yeah, I think our graph checks out. That looks good. Let's try another one. Okay, so our function to graph here is x to the 4th minus 6x squared. It's another polynomial function, so we have the domain of negative infinity to positive infinity. First and second derivative are going to be easy to compute here. So we'd get 4x cubed minus 12x. And for the second derivative, we would get 12x squared minus 12. Okay. And we don't have any places where either the first or the second derivative are undefined because they're both polynomials. So we just have to figure out where these derivatives are equal to 0. So 4x cubed minus 12x being equal to 0. We could factor an x out of that and a 4 if we like. And we'd have x squared minus 3. And so set those two factors equal to 0, and you're going to get x equals 0 and x equals plus and minus the square root of 3. So we've got 3 critical points. If we set the second derivative equal to 0, then we see pretty quickly that x squared is equal to 1, so x is plus or minus 1. So 2 possible inflection points. Let's figure out what's going on by looking at a sine chart. So for the sine of the first derivative, we're going to be worried about x equals 0 right here in the middle, and then plus and minus the square root of 3, which is like 1.7. So we'll put that a little bit further out here like this. So negative square root of 3, positive square root of 3, and 0. And we're going to check the intervals between those numbers in red. And then we're going to look at plus and minus 1 on the second derivative. So let's check the sine of the first derivative. Okay, if I plug something less than negative square root of 3 into the first derivative, let's say negative 2, for example. If I put negative 2 into the first derivative, I'd get 4 times negative 8, so negative 32, and then minus 12 times negative 2, so that'd make it a plus 24. So I'd have negative 32 but plus 24, so it'll be negative over here. And then we could plug negative 1 into the first derivative to test the next interval. So you plug negative 1 into the first derivative, you'll get negative 4 and then plus 12, so that's positive. And then let's plug positive 1 into the first derivative to check the next interval after that. And you'd get 4 minus 12, so that's negative. And then you'll get a positive on the next interval by plugging in some big value, because x cubed is dominant. All right, and then we'll do similarly, plug numbers into the second derivative to check these intervals. If I plug negative 2 in there, I would get a positive value. And then if I plug 0, that would be intermediate, I'd get negative. And then I'll get a positive over here. Okay, so I can see from this sine chart, I didn't write it last time, I didn't spell it out in words, but what we see is it's increasing on negative square root of 3 to 0, and then square root of 3 to positive infinity, and we see it's decreasing on negative infinity to negative square root of 3 and 0 to positive square root of 3, and I can see it's concave up on negative infinity to negative 1 and 1 to infinity, and it's concave down on the interval from negative 1 to positive 1. And then for this particular function, since they're polynomials don't have any horizontal asymptotes. So it's just going to be going, it's just determined by looking at the leading term of x to the fourth. And so just shorthand, this thing's going up on the right-hand side and down on the left-hand side is the end behavior. And there are no vertical asymptotes because we're not getting any division by 0 or anything like that. And then the local extremes we can see from the sine chart. So we can see minimum at negative square root of 3 and at positive square root of 3. And I can see I'm getting a maximum at x equals 0 just from looking at the sine of the first derivative. Inflection points, I can see, I've got inflection at negative 1 and at positive 1. X-intercepts, could we easily set that original function equal to 0 and solve for x? I don't know, let's see. Looks like it won't be too hard. X to the fourth minus 6x equal to 0. Or is it 6x squared equal to 0? Yeah. You get factor out of x squared, and then you'd have x squared minus 6 equals 0. So you're going to get x equals 0, and then x equals plus and minus the square root of 6. And the square root of 6 is, a little more than 2, but not quite 3. And y-intercepts, if you plug x equals 0 into the original function, you get y is equal to 0. So just the origin is the y-intercept. Okay, so again, I think we have enough information to start graphing this thing. So let's do it. I'm going to make the x-axis go out to plus and minus 3 because the biggest x values I see in my list of special points are plus and minus square root of 6, which are between 2 and 3, positive and negative. So I think if I go out to -3, I'll get a big enough window on the x-axis. I don't know about the y-axis. I need to plug in some test values. Like, what if I plug in, what's going to happen at the square root of 3 with that function? It's like, what's f of square root of 3? Well, f of square root of 3 will be 9 minus 6 times 3. So -9. So I think I'll just go to, like, say, positive and -10 on the y-axis. Okay, so now I know that we have a minimum at both negative square root of 3 and positive square root of 3. So that's like 1.7-ish. So that'll be somewhere about here. So this point is negative square root of 3, -9. And then I have something happening at positive square root of 3, -9. And then at square root of 6, what do you get when you plug square root of 6 into a calculator? About 2.45. So somewhere in here and here, at square root of 6, we get our x-intercepts. Now also, when x is equal to 0, we're having a local maximum. So I'm starting to get the shape of this graph here. And it's also an inflection point at 1 and -1. So let's figure out what is f of 1. F of 1 is 1 minus 6. So -5. So, and you get the same thing when you plug in either -1 or +1. So that's about here and here. So those are my inflection points. So I'm starting to get a pretty good sense of what's going on here. It's coming down like this, goes through the x-axis, bottoms out at that point. It's still bent upward until it gets here. Then it starts being bent downward. It peaks here at the origin, comes back down, still bent downward until you get there. Then we have inflection. Then it's bent upward again, bottoms out, comes up, goes through that intercept and out again. So we have here 1, -5, -1, -5. So these were inflection points. Here and here. Here we had local mins and local max here at this point, which is 0, 0. Yeah. So at this point, I think we've got a pretty good, decent idea of what that graph looks like. And now if we wanted to go to the technology and check our answer, let's do that. So we're going to do x to the 4th minus 6x squared. Let's straighten it out this way a little bit. You know what? That looks really pretty close to what we just graphed a second ago. So I'm feeling pretty good about that. You can see those inflection points at -1 and +1 here in this graph. You can really see where the way the curve is bent changes there. And yeah, we can see. Just to be sure, I plotted those special points to see if they fell where they were supposed to. So I plotted the inflection points that we found analytically, -1, -5, and +1, -5. And you can see, boom, they're right there on the graph, right where they look like they're supposed to be. I plotted those minimum values at negative square root of 3, -9, and positive square root of 3, -9. And we can see, yeah, they look right on the money. And then I plotted the x-intercepts at negative and positive square root of 6 on the x-axis. So yeah, the thing that we graphed by hand a second ago was really on the money. Look at it. Yeah, my hand's a little wobbly here and there, but not so shabby. Let's try one that's a little harder, maybe involves fractions and stuff. Okay, here we have a rational function, 3x over x squared minus 1. Let's figure out what this thing is doing graphically. Now in the domain of this one, we know with rational functions, the domain is just all real numbers except for where you get 0 in the denominator. So this is going to be all reals except x equals plus and minus 1 is where you get 0 in the denominator. So I want to keep that in mind. We've got these isolated places in the domain where the function has 0 in the denominator. So we won't be surprised to find that there's an asymptote there, a vertical asymptote. Okay, now let's calculate our derivatives, first and second derivative. So if we use the quotient rule, we'll get 3 times x squared minus 1 minus 3x times 2x all over x squared minus 1 quantity squared. And if we simplify that a little bit, we're going to get 3x squared, and then there's a minus 6x squared, so that'll be minus 3x squared, and then a minus 3, all divided by x squared minus 1 quantity squared. I'll leave it at that. And for the second derivative, we have to do the quotient rule again. And so the derivative of the top here would be negative 6x. Then we have to multiply times the bottom. So x squared minus 1 quantity squared minus, and then the numerator, negative 3x squared minus 3, and then the derivative of the denominator would be 2 times x squared minus 1 times 2x, and that gets all divided by x squared minus 1, and then to the fourth now, because I took what was there in the denominator before and squared it. We may want to simplify this just a little bit, because we are going to have to figure out in the next step where that's either undefined or equal to 0. Okay, so, and then going off to the side a little bit and doing some simplification, I found out that the second derivative reduces to 6x times 3 plus x squared divided by x squared minus 1 to the third power. Okay, let's figure out where that first derivative is either equal to 0 or undefined. Here's your first derivative in yellow. So, first of all, let's think about where it's undefined. It's undefined where that denominator is equal to 0. That's at plus or minus 1. Now, those are already points that we've made note of are points where the function's undefined. So, we kind of already have those numbers accounted for as points we need to be thinking about, because we're always going to think about where the function is undefined, especially if it's isolated points. So let's just figure out now where the derivative is equal to 0. Well, I can see that this is just not going to happen. I mean, if we reduce this down, it becomes x squared equals negative 1. So that never happens. So interesting, this function has no critical points. Now, that doesn't mean that the derivative can't change sign somewhere, but it just means it's not happening at what we call a critical point. It may be happening at a place where the function's undefined, though. Now let's see where the second derivative might be equal to 0 or undefined. Again, the second derivative is undefined at the same places where the original function is just not defined. So we kind of already have a bead on those points. So let's figure out where the second derivative is equal to 0. Well, that fraction will be equal to 0 when its numerator is equal to 0. So right now we're looking at this fraction in green. That's the second derivative after we've simplified it. So we set the numerator of that equal to 0. Well, the second factor here can never equal 0. 3 plus x squared is always positive. So the only way this is going to be equal to 0 is when x is equal to 0. So there's a potential inflection point. So what points do we have to think about on our number line? Well, we got that place where the second derivative is equal to 0, x equals 0. So this point, let's put it right in the middle here, 0. And then also there are the places where the function was undefined, and both the first derivative and the second derivative could change signs at those places. So at plus and minus 1, both of these, I'm going to put a bar that goes all the way through, both the first and the derivative, first and second derivatives could change sign at these places. So let me mark them for both. Now, if I check the sign of the first derivative on the top side of this line, okay, remember the first derivative, what is the first derivative equal to? The first derivative was negative 3x squared minus 3 over x squared minus 1 quantity squared. You don't need to worry about the denominator here so much because it's always non-negative. So really you just need to, when you plug in your test value, you plug it into the numerator and see what you get. So if I would plug negative 2 into the first derivative, I'm going to get a negative value. And if I would plug 0 into the first derivative, it's going to also be negative. And if I plug something bigger than 1, say 2, it's still going to be negative. So it's just negative. So this thing is decreasing the whole time. How strange. How could it be decreasing the whole time? Well, I guess it can happen. Well, we'll check in a little bit with our graph to see if it's doing what it's supposed to be doing. Okay, let's find out what's going on with that second derivative. Now the second derivative, as we saw, was 6x times 3 plus x squared all over x squared minus 1 cubed. So I want to test the interval to the left of negative 1. If I plug, say, negative 2 into the second derivative, I would get negative 12 times something positive over something positive. So that'll be negative. So second derivative is negative over here. Does it change if you put in something between 0 and -1? How about -1/2? If I put -1/2 in there, I'm going to get negative times positive over negative. So I'd get 3 times something positive over something negative. -3 times. So yeah, this is going to be positive here. And then if I plug in something between 0 and +1, say -1/2, +1/2, then I'd get something positive times something positive over something negative. So this is going to be negative here. And then if I plug in a big positive number, it's going to be positive over here. Okay. See how important it was to have the place where the original function was undefined on our number line. Let's look at our end behavior and talk about any vertical asymptotes. So for end behavior, if we look at our function, the degree of the denominator is 2 and the degree of the numerator is 1. So that means that the denominator grows big more rapidly than the numerator. So as x gets large, either positive or negative, it's going to get close to 0 in the limit as x goes to infinity. So if you take the limit as x goes to either plus or minus infinity of our original function, you're going to get 0. So that tells me that y equals 0 is a horizontal asymptote as x goes to infinity and as x goes to negative infinity. And for vertical asymptotes, we want to look at those places where we get division by 0 and see what the limit is there. So let's see what's happening around x equals plus and minus 1. So if we look at the limit as x approaches 1 on the right of our original function, which was 3x over x squared minus 1, well, I can see that the numerator is getting close to 3, and the denominator, since I'm putting in numbers a little bit bigger than 1, would be going to 0 but positive. So this is going to be positive infinity. And similarly, I could look at the limit as x goes to 1 but from the left. And this time, since the denominator is going to be going to 0 but negatively, and the numerator is going to positive 3, I'm going to get negative infinity. So I've got a vertical asymptote here, and I can see what's happening on either side of the asymptote. On the right side of the asymptote, it's going upward, and on the left side, it's going downward. And we need to see what's happening around x equals -1 too. So -1 from the right. Okay, here it's going to be going to -3 in the top, and then, okay, if I take a number that's a little bit bigger than -1, like -0.9, I'm going to get negative in the denominator. So this will be going to 0 but negative. So this is going to be positive infinity because it's going negative in the top, negative in the bottom, but the bottom's going to 0. And if x goes to -1 on the left, it's going to be going to -3 in the numerator, but if I'd put in a number like -1.1, that gets squared, and that gives you the bigger value in the denominator, so it'll be going to 0 but positive in the denominator, so negative over positive, this is going to negative infinity. Okay, so yeah, I see vertical asymptotes, and I can see what's going on around them, so that helps me know what the graph's going to be like. Local extremes, from our graph of the first derivative, we see there were none. The sign of the derivative never changed at a point in the domain of the function. So none on local extremes. Now, the places where we have asymptotes, so we just discovered through looking at these limits that 1 and -1, those are asymptotes. So I wouldn't consider them to be inflection points. Even though the sign of the second derivative changes at those places, they're not inflection points. But we do see an inflection point happening at 0 because that's a point in the domain of the function, and the sign of the second derivative changes there. So we see an inflection point at 0, 0. 0 is the y value when you put 0 into the original function. And what else do we have here? X-intercepts. If we take the original function and set it equal to 0, you'll pretty quickly see that it's going to be, you get x equals 0, and then that has a y value of 0. And also the y-intercept, we just discovered it because 0, 0 is where x is equal to 0. So, okay, it's interesting. So we got a graph. The interesting behavior is happening at +1, -1, and 0. So that tells me how to scale the graph up. So there are my asymptotes that I know I have at -1 and +1. I know that at the origin something interesting is happening. There's a point of inflection there. Now let's figure out what's happening between these asymptotes. I know that it's going to positive infinity. It's going to positive infinity on the right side of -1. On the right side of -1, it's going up, up, up like this. And on the left side of +1, it's going to negative infinity, so it's going down, down, down here. And then there's inflection at the origin, and the nature of the inflection is that it changes from concave up to concave down, as I recall. Yes, it goes from positive to negative on the second derivative at 0. So it's bent upward, and then it hits the origin, and then it's bent downward, and then it heads down to negative infinity as it goes toward that asymptote. So this is roughly what it looks like between -1 and +1. Now what's it doing out to the left of -1? Now we know from the part in green over there about the end behavior that it's got a horizontal asymptote of y equals 0. In other words, the x-axis is a horizontal asymptote. And then to the left-hand side of -1, it's going to negative infinity. So it's going down, down, down over here to the left of that asymptote at -1. And then it's got to be getting close to 0 as x goes to negative infinity. So it looks like it's going to be doing something like... Now we could make this more accurate by plugging some test points. Like I could maybe plug in -2 or -3 just to get a few y values out of it. But I think this is going to give me a pretty good sense of it. Now also the way I've drawn that, it looks like it should be concave downward there, but let's check. Yeah, we see that to the left of -1 on our sine chart up there, it's concave downward. And if we go to the right of the asymptote at x equals 1, we see that the function is going to positive infinity. So let me put a little bit of the graph there like it's going upward. And then we know that as x goes to positive infinity, y equals 0 is an asymptote. So I think it's going to do something like this. It's going to have that horizontal asymptote on the x-axis there. And again, I could make the graph a little bit more accurate by, plotting a few test points in between. But I think, I've got the sense of what the shape of the graph is here. I understand its behavior pretty well. I want to double check, is it concave up to the right of 1? Yeah, on the green sine chart up there at the top, you see that sine of the second derivative is positive in the interval from 1 to infinity. So yeah, I feel really good about this. I'm pretty sure when I go plot this on the grapher, it's going to be like that. Okay, so let's plot it. It was 3x over x squared minus 1. Look at that. That matches what we did pretty closely. If we wanted to see more of the y-axis, we could stretch the y-axis here a little bit so we can see the asymptote a little bit more clearly. Yeah, you can see negative and positive 1 are asymptotes, and wow, it behaves just like we thought it did. You can see the inflection at 0, 0 there, right? Very cool. Okay, I think that should give you enough information about how to do these. We've done 3 examples. Key thing is just to take your time. Don't be in too big of a rush. And yeah, by all means, check your answer on the computer. But I would encourage you to see if you can do the analytical approach first and figure out what all that behavior is. Then check your answer, and if it doesn't match up, then maybe you made a mistake calculating one of the derivatives or computing a critical point or whatever, and you can go back and check that. But yeah, see if you can make it match up. Okay, I'm going to stop there. I'll talk to you again soon. Bye-bye.